Hello, in today's video, let's talk about a PDK or a process development kit. So before we do that, let's revisit what a product design flow typically looks like. So the design usually starts with a product definition, followed by planning, and then the actual synthesis of the design happens. And that begins with an RTL design, followed by logic synthesis. Based on that logic level design, a gate level netlist is generated, followed by which you have a standard cell placement and a layout done. Once the layout is done, then verification occurs to ensure that the layout matches the RTL design. Now, once that is done or this design is completed with its pre-checks, it then goes into the fabrication phase. So the design, the layout are then converted into mass. So that happens through what is known as mass generation. And prior to mass generation, two important steps happen. One is known as an OPC or an optical proximity correction, and the other is a DRC or a design rule check. Right? And when both these are needed to ensure that the masks are faithful to design, to ensure that what we get on silicon is faithful to the design. And then fabrication of the wafer happens. Once the fabrication happens, the next step, it goes into testing. So you want to make sure that what you fabricated is actually works as it intended to. So we find a functional wafer, we test its functionality, make sure it's in line with what we had intended for the design to work at. And we also do what is known as reliability testing, which means that stressing the wafer or stressing the chips at higher temperatures so as to ensure that they can withstand the lifetime of the product. Following that, it goes into the packing state where we do a dicing and sort. So this wafer level chips are then put into a package, primarily to ensure there's no wear and tear for easy mobility, and to then we have it put into assembly. And once that is done, we actually build boards, and so you create your PCB, and then you do system level integration, which is basically system assembly and system testing. So two types of testing occurs, one at the wafer level and then one at the system level. So what's a PDK? A PDK stands for a process design kit, and it contains basically all the process related information. So this is something that the foundry will supply to its customers. So if you're a design house, this information is given to you by the foundry, and it's used to model any process related effect using what are known as EDA or electronic design automation tools. Now, PDKs are used for planning, they're used in design, and they're used in verification. And all this happens prior to fabrication, right? So typically, if you look at the timeline of products, this happens probably a year or two prior to actual tape out at the foundry. And the expectation from a design house, suppose you're doing a design, your expectation would be that this initial pre-work you're doing prior to taping out the design. And remember, design tape out is a very expensive process, right? And depending on the node you're working in, this can be a multi-million-dollar project. And so to ensure that you have good success in your first attempt, it's important to ensure that this PDK captures all the information of the process, reliability, and in a conservative fashion, so that your simulation to silicon gap when your first silicon comes out is small, so it's predictable, right? And hence it's important that the PDK must be of high quality, because the quality of the PDK is going to determine what is the success that you'd get in the first pass. Remember, yield improvement, process improvement is a continuous improvement process. But what you want is your first pass silicon, you want it to yield. After that, you'll introduce further process improvements, further design improvements to improve the yield of your particular product or chip. So what does the PDK typically contain? So it contains all the device libraries. It contains the technology data and the tech files. Now, tech files are essentially files needed to do the extraction for, say, back end of the line. It also provides a reference flow and some demo kits, right? Especially if you're starting something on a new process, or suppose you're moved, for example, an important transition happened when foundries moved from planar to FinFET technologies, right? So for a design house, when it first started using FinFET technology, there were a lot of demo kits released so that designers could learn FinFET specific design considerations that to be taken in when you're designing the process flow. It also contains simulation models. It contains standard cell libraries, abstracted views, and device characterization libraries. And all these are important to ensure that your circuit works, or you use these to design a circuit that will actually work. And very importantly, it contains what is known as a design manual, which is going to contain all the rules and all the process related information and all documentation necessary to ensure that your design is foolproof before it goes into the foundry. Finally, the PDK, multiple vendors exist for EDK tools in the market, and your PDK has to be able to work on all different EDA tool sets. So typically, the foundry would release PDK specific for different EDA tools. So how does one build a PDK? So first thing is as a foundry. So this is done at the foundry end of the market, right? Because say a TSMC or a Samsung or an Intel or Global Foundries or any of the foundries that are available, right? They are going to build a PDK for their customers. So they initially start with the market study, figuring out what is it that most of their customers need. They look for input from customers as to what is the next process one is looking at, what are the kind of features one would need. And obviously then they have to create a business decision for this, right? Whether it is profitable to enter a particular node or a particular design space. Once that is established, the next step is actual technology development. So here you actually come in and start thinking, what are the features of the design of the process? What are all the transistors that's going to be supported? What other features are going to be supported? So you define, the device list. What are the kind of transistors? How many VTs? What are you going to support? BJTs? Are you going to support other memories on it other than SRAM? The kind of metal stack you're going to offer, the different kinds of device types, and also an idea of what the parameters on the device you're going to offer, right? So once that is done, the next thing that happens is you have to now generate silicon data. So this is all based on market intelligence, based on some very prior silicon data. And now you have to go in and actually prove this on silicon, identify what are the gaps, what is possible on silicon, what are the new materials, what are the new structures one needs to put in so as to achieve this particular set of goals, right? And so you create test chips, you create shuttles where you run continuous wafers, run experiments, and try to develop a process technology that is going to deliver the kind of device performance that you have committed. And here again, you generate the silicon data, you look at device performance, compare device performance to targets, figure out ways by which you close the gap between the two. You look at metal stack data, look at R's and C's, ensure that they're within targets. If not, think about what are the right techniques to be used to get to the targets. After that, once all this silicon data is generated, we then next go into PDK development, right? So whenever you look at PDK, remember a good PDK ensures good first pass silicon. Therefore, a PDK has to be developed off silicon data, and this silicon data gives an idea as to what is the process that's going to run on the first silicon, right? So this PDK development essentially needs a lot of silicon data generation so as to put faith in the PDK that it is going to eventually be something that can be done repeatably and with high yield in the high volume manufacturing. And now during PDK development, you also have various specific pCells or various new structures that you'd like to enable in this particular technology. And you'll have new rules, you'll have new devices, you'll have new parameters. Again, these would be something that would come from this initial step. So you'll do all this on the test step. Sometimes a lot of this is going to be done for the first time on a specific PDK. So there's going to be a couple of cycles of learning so as to get this down right? And then you release the PDK to product development. And once you do an initial product, so typically all PDKs, all new technologies have a flagship product which is going to be the flag bearer, if you will, of the new technology, and that runs through the fab in the first pass. And so you actually get feedback from that, from silicon, from that particular product. And so it's an iterative process that you need to go through a couple of product cycles, a couple of test chips, multiple back and forth. So this PDK, if you think about it, has different versions. A foundry, when it initially starts, is going to release a PDK with a lower confidence. And as the foundry learns more from silicon and it does a lot more of experimentation, as it begins to close the gap between the targets and what actual silicon is going to provide, the PDKs become more predictable, and so the quality of the PDK improves. Now, what is a design manual? So, a design manual captures all the semiconductor process and process design kit information for setup and deploying all the necessary flows required in setting up a design flow. So this would be instructions to install the PDKs, technology overview, what are the kind of devices you're supporting, what are the kind of metal stacks you have, what are the kind of supply voltages, what is the kind of packaging you recommend, etc. We also look at metallization options with pitch and spacing. Again, this is something, you go back and forth with the foundry. If you need special requirements for your product, then you need to work with the foundry to ensure that that's being enabled on a particular process node. We also have device truth table. Now, device truth table basically means that typically you want to share litho layers. Remember, one of the most expensive processes in fabrication is creation of masks. So you want to reduce the number of masks in the process flow if you can, which means that as you support multiple device structures, multiple device flavors on the technology, you try to share mask layers across different types of devices. And so there is something known as truth table that is available. So for example, it tells you what are all the CAD layers necessary to build a certain device. So this information again is shared. And again, there is a lot of scope for customization at these various steps depending on the kind of relationship the design house has with the foundry. So you also enable special flows. As I said, these are custom specific flows for your particular product. Obviously, they come with a cost. So if you're able to support that, if your product is able to support that high cost, then the foundry will work with you to enable those customizations. Layout design rules are important. So as I said, this is important and critical to design a mask that is able to give you yield-worthy silicon. So this gives you the kind of design rules that you need to follow. Similarly, you have a bunch of rules required to create devices, and so that would be part of the design manual. Specific structures like ESD and Latch-Up would require additional rules, and those will also be part of the design manual. Reliability, right? What happens as transistors age, as metal lines age, is also released in the PDK, and specific rules are available if you need to meet specific targets. And then models and model parameters for transistors, for RF devices, etc. are part of the kit. And then also dummification, metal fill, etc. Those are also guidelines are available in that particular design kit. And you have any specific differences in the digital analog flows, those are also going to be highlighted in this PDK. Now, what's a pCell? We come across this term pCell, which is nothing but a parameterized cell view. So many a times the foundry releases the layout of a particular cell, and the layout is not fixed, but rather it's a customizable layout. So you can directly plug this layout into your designs, and this becomes especially useful when you start looking at analog flows or RF flows. And normally it contains a lot of devices like resistors, FETs, inductors, etc. And the ability to parameterize allows you to specify and look at designs as you optimize the designs for certain analog requirements. An important part of the PDK is known as the design rule check. Now, as I said, DRC rules are a set of parameters that need to ensure correctness in the design of mask. For example, a simple design flow would be that you normally create a transistor by an intersection of the poly with silicon, right? So this is your active and this is your poly. The poly and active have to intersect to create a self-aligned MOSFET. And if the poly does not overlap the active, then it's possible that you're going to have a source drain that are shorted. So one of the most simple design rules would be that the poly cannot terminate inside an active. So the poly always has to have a certain overhang, or it should overlap the active, right? So that's one of the simple rules. So a DRC there would specify that, so that will always ensure that no matter what is the worst case registration error between the poly and active, in the worst case you're going to ensure that the poly still has an overlap of the active. So in no instance are you going to get a case where there is going to be a source and drain without the poly completely isolating the source from the drain, right? And typically there is a run set that the foundry releases, and designers use that to validate their designs. And as I said, when you build custom flows, some of the design rules will need waivers, will need redesign. So that's again a process that is iterative, that you work with the foundry to generate. Especially if you look at post 12 nanometer and 10 nanometer nodes, there are, for example, poly, fin, etc. have multiple layers, right? So a single fin structure, poly structure, actually has multiple litho layers behind it. So you have specific rules pertaining to these layers, which are not actually available to designer, but something that designer needs to keep in mind as they are generated. And there are different kinds of rules in a DRC. Some of the ones I want like to call out are specific spacing, width, and enclosure. So how close can two lines be in a particular design? For example, two metal lines. You don't want them to be too close by because you run at the risk of shorting, you run the risk of running a high capacitance, and you don't want the metal lines to be too far apart because then you're going to lose area. So there's always a certain spacing rule, for example, you have between metal lines. Similarly, you have rules for width, right? For example, if you think about a metal line, again, there is for a given technology, based on the particular kind of process they're using for deposition of the metal, it dictates what is the aspect ratio of the metal trench, if you will. And so therefore you want to ensure that in the worst case or in the narrowest metal trench, the process that you've developed for this particular node is able to fill in that metal and not cause any voids, because a void in the metal line essentially leads to a high resistance, right? So there are rules related to what is the smallest width one can draw in the metal line and so on and so forth. Similarly, as I mentioned with the poly and active, you have enclosure rules, how certain layers have to interact with other layers to ensure that the device functionality is not lost. Then you have very specific rules related to antennas and related to, for example, high voltage, especially when you're doing SoC where you have multiple voltage domains on a chip. How do you deal with transitions from one domain to another domain? So that's again something which you have to be very careful about. Again, why does this all come up? Because remember, when you have higher voltages, the fields are going to be more. And physically, this means that you have capacitors which have high electric fields. And you want to ensure that in the worst case, there is no breakdown of the capacitor, right? So these rules come into play there. Then you have things about ESD and Latch-Up rules. Again, these are specific as you deal with interfacing to the I/O. And then you have rules for poly, metal fill, etc. These are to ensure that there is a fidelity between design and process. So a lot of dummification is needed, especially as you scale technologies, to ensure that your design is faithful to what you've drawn on your layout editor. And remember that a lot of our flows are automated. As I told you, you write an RTL design and then the tool comes in and converts it to a gate netlist and eventually standard cells. And most of the digital designs run this way, right? Now, obviously, if it's something which all competitors are going to use, then you're going to see that there isn't a lot of difference in design. So obviously critical parts, you're going to try and see if there's some way by which you can make your design more competitive, right? And that would involve, sticking cells closer, playing around with the spacing rule somewhere here and there. So eventually you're going to be editing some of your layouts, right? Again, to make your design competitive. Now, when you do that, you need to ensure that the final layout that you have does not sway too much away from the schematic. So you have what is known as a layout checker, which is going to ensure that your final layout does not diverge away from the schematic that you've initially planned. And there are various tools across various EDA vendors which do this. And this is known as an LVS, a layout versus schematic. And these include things like layer and data types, device definition. So the tool needs to identify what is the particular device you have in the layout, and then go back, look at the pins, and then go back to the schematic and ensure that those pins and that particular device is connected in the fashion that you required in the schematic. Then the layout LVS should also be able to extract the device properties, right? You're going to specify a particular W by L on the schematic. The layout tool needs to be able to extract that W, needs to extract that L from the layout and ensure that that matches the particular schematic. And then you need to worry about over spacing structures, stress structures, etc. So all those go into the LVS because stress, LOD, etc. are layout dependent effects. So these things need to be captured and they need to be fed back into the schematic because that might change the model that is applied for your simulation. And finally, you need to worry about device merging, reduction, filtering, etc. A short slide on the electrostatic discharge structures or ESD. So typically when you have a chip with varied voltage levels, sometimes a freak incident like a charge coupling, right, can induce a rapid transfer of charge between two different circuits. And typically what that means is that, or there's a spiking, there's a sparking, if you will. And so that ends up creating a large instantaneous electric field, most probably across a dielectric. And one of the most critical dielectrics in our circuit is obviously the gate oxide. So if this happens across a particular gate oxide, right, then all of a sudden the MOSFET gate, which was insulating, can end up being conducting, right? And so in that case, the gate, there is a leakage current that goes from the gate into the source or the drain. And that can cause a failure on the circuit. So you need to ensure that there are specific rules available so that the probability of this electrostatic discharge happening, you need to reduce it to as much as possible. And so specific protection structures are available. And typically these are made up of Zener diode-like structures or reverse bias diode structures, which will essentially break down and so as to shunt any additional charge through those structures to prevent any breakdown of the structures of interest, right? And you also have BJTs and FETs, etc., used for the same purpose. And again, these are very technology specific structures, and so they would be available as a part of the PDK. And this is known as a programmable electrode checking, and that is used to basically look at the discharge path in ESD and then used for sizing up the devices in the ESD path. Another second order effect, if you will, would be an antenna effect. Now this happens during the process. So suppose you have a gate and you have multiple metals connected to it. So every time this metal layer is fabricated, basically the wafer is stuck in a plasma when you create these metal structures, trenches, vias, etc. And a plasma is nothing but a high energy system, and so there is charges with high energies floating, and this forms an antenna. And so what happens therefore is that charge can cause an electronic discharge directly at the gate, and this is amplified. Suppose you have a lot of metal area exposed to the plasma, right? And so this is known as an antenna effect. So you need to have special rules to check for the specific metal nets connected to a gate, and then to ensure that these nets do not cross a certain area so as to prevent the occurrence of any electronic discharge at the specific gate, right? And typical fixes use metal jumpers, use antenna diodes. Again, diode is a similar fashion. We use a diode to shunt any additional current that can occur. And the other way is also to think about specific rules available where you don't allow the gates to be very long. So you reduce the probability of gate oxide breakdown in that case. You also have the issue of latch-up, and latch-up is something we've looked previously in other videos where, especially if you look at the twin well technology, right, you have an N well and a P well in a P substrate. And so you have these parasitic BJTs formed, a PNP and an NP and BJT. And this, if there is a breakdown in any one of these large junctions, then this NPN PNP diode can actually become forward bias, causing a huge current to flow between the wells, right? And so that can cause an essential failure in the circuit. So you need to ensure that this latch up is prevented. And so there are specific rules available for latch up, and those would include adding some trenches in between or creating what are known as guard rings, especially when you have the possibility of a large voltage difference between two wells, if you will. At high current densities, electronic flux, there is electromigration that can happen in the back end, right? So if there's a large current flowing in the metal line, then that the flux generated because of the electric field and the motion of electrons can actually displace metal atoms, leading to shorts in the metal stack. And so you need to figure out a priori if there is a risk involved, right? And so this electronic migration, when you run test chips, you kind of know how this electron migration varies as a function of the dimension of the wire and the thickness, etc. So the various levels in the metal would have various thresholds. So you need to have a rule to check and ensure that for a given current density, you restrict the metal line to a certain dimension so as to prevent the risk of electromigration. And so the tool, you have an electromigration tool which is going to check for maximum current densities, and it's going to compare and ensure or check whether there is a risk of failure due to electromigration and flag it for you. So either then you go in and fix it, or you figure out if there are other circuit designs that you can employ so as to reduce the effect of that electromigration. And the tool also computes the IR drops. Remember, when you looked at interconnects, the resistance of the interconnect lines become important, and the larger the resistance of the interconnect lines, I'm going to have a sag in the rise and the fall time of a digital signal as it travels through the interconnect. So knowing what that IR drop is, and either you're able to correct it a priori or you figure out a way to work with that in the design, is something that is flagged by the tool. It's up to the designer to figure out how to fix for the same. Another important issue which occurs in most devices is self-heating. Remember that there's a lot of current that flows to MOSFETs and high current densities. Same thing happens in metals. So high current densities, high electric fields basically causes wear and tear in the materials, which means that your MOSFETs are essentially aging. And that means that aging means bad things happen, right? Your MOSFETs are going to change BTs, they're going to reduce IDs, etc. So this degradation needs to be captured, because you want to ensure that in the lifetime of the device that you've promised your customer, your circuit functions. So your degraded transistor, the circuit with the degraded transistor has to also work within the 5-year or the 10-year lifetime that you have for your particular product. And electromigration also increases with self-heating, so you need to ensure that special structures need to be added. For example, if you find a hot spot on the chip and you need to reduce the local temperatures, and typically temperature management is done through vias. A very simple way of reducing temperatures to create these dummy via structures. And what vias do is they are made up of metals, so they're able to conduct heat quickly away from this hotspot. And so there are specific rules associated with via densities which can be employed when you're dealing with self-heating. And then, as I mentioned, when you have multiple voltage domains on the chip, you need to ensure that you have a DRC checking available, specifically which is able to identify the voltage on the net and look for specific spacing and width rules for those domain checks. And this is known as the voltage aware DRC, and that is critical for an effective check on the DRC. And as I mentioned, based on this voltage difference, remember, depending on the number of voltage domains you support, the spacing limits might change, the metal spacing limits might change. So again, when you have this voltage aware DRC, you're able to flag if certain nets are of high risk. Now, quick note on the device models. So most of the models in modern PDKs are compact models, typically BSIM models, and they are basically fit off the measured silicon data. So any model that the foundry releases is based on some silicon that they've run at least a couple of times to ensure that they're able to repeatably produce that silicon data. And these are run over what are known as corners, so over permitted design variables like LW, TOX, doping, standard MOSFET parameters. The foundry runs those corner lots to ensure that they're able to generate or they're able to guarantee what is the target or the nominal model and what is the worst case and the best case model available. Now, the model, as I said, is a compact model and it includes all the essential physics required for modeling. Right? And many a times, a lot of the models you'll see, if you look into the model card, there are a lot of empirical models associated, and those are primarily done, one, because the physics is too difficult to model, and two, because you want to also keep this computationally efficient. We are not dealing with one transistor, we're dealing with millions of transistors. And especially when you start doing Monte Carlo simulations on top of them, then it's important that your device model remains computationally efficient. And so there is a trade-off that plays between what is the kind of physics one can model versus how to keep it at a realistic time frame. And as I mentioned, these model versions change, if you will. So as you start the technology, if you're an early adopter of a technology with the foundry, you're going to be given models with limited silicon data. And so therefore, the foundry tells you that I have limited confidence in them. And as the foundry learns with more silicon on that particular technology, it improves the models. So an example would be that in the initial models, there might be a huge variation that is put in between the weak model and the strong model, say for a transistor. And as the process matures in the foundry, you'll see that this variation reduces, right? So therefore, the model, if you will tighten as the nodes, as the foundry learns more on the node. Or another way to look at it is if you're adopting, say, a 2 nanometer node versus a 10 nanometer node, you'll see that the variation for a 2 nanometer on 18 node is going to be more than the variation for a 10 nanometer node, just because the foundry has probably not worked on it for long. As the process technology matures, the variation reduces. And again, similar to that silicon model, the initial aging models also are guesstimates, and as you get more and more silicon data, the foundry firms up on the aging model and releases models which track silicon performance. So if you look at device corners, we've looked at it in other videos. We typically look at the NMOS drive and the PMOS drive. We have the nominal corner model here, which is the TT, and then you have typically 4 corners, the FF, SS, SF, and FS. We also run Monte Carlos on all designs, and Monte Carlos typically span this place around STT, and generally the FF and the SS are the worst of the worst cases. So many times you'll see that designs may not close at FF or SS, but slightly less, depending on how much the design house trusts the Monte Carlos to how much you trust the corners. So again, that's something that comes with experience, that comes with the confidence the foundry has in delivering silicon data. So it depends on how many years the particular technology has been running in the foundry. Finally, there are a lot of additional features that can be put in the PDK, and you'll see that when you look at different foundries, those kind of tend to differentiate the foundries, and that also gives the design house the option of choosing a foundry based on which feature is particularly attractive for your particular product. So electromagnetic models are available to model inductors, especially if you have SoCs where you want to put inductances on the chip. You also have special models released for RF design and mmWave models, and these have specific BUL stacks or different pCells depending on the kind of performance you need from the MOSFET. You'll see these days that a lot of PDKs also contain packaging components, especially as we move to 2.5D and 3D integration. You'll see that these become large components of the PDK. And so you'll see that the foundry bring in rules for 2.5D, 3D packaging in the subsequent technology nodes.